So, good evening and happy Engineers Day to all of you. I would like to right away request Professor Sandeep Trivedi, Director TIFR, for a few words of welcome.
Well, it's a great privilege for me to welcome our speaker this evening, Professor Subhasis Chaudhuri, who's a very well-known computer scientist and engineer, and also now the director of IIT Bombay. Welcome, Subhasis.
Thank you.
It's a special privilege to have you as our speaker in the Asset Colloquium on the occasion of Engineering Day, when we celebrate the memory of one of India's greatest engineers and draw inspiration from his life. And we really do look forward to your talk, which is very topical also, Subhasis, on machine learning. Attracts a lot of attention now, even in our students in the sciences and so on. And of course, for this topic, computer science and mathematics and engineering, they all come together. So we're all looking forward very much to hearing your talk and getting your perspective. I also take this occasion to welcome some of the others who are joining us. Professor Dipan Ghosh, of course, needs no introduction to us, but he's been a pillar of support for TIFR and the Alumni Association to welcome. So welcome to you as well, Dipan.
Thank you.
And everyone else who joins us over YouTube today on this very special occasion, a very warm welcome to you all on behalf of the entire TIFR community. And I hope you will continue to log into our YouTube channel and follow the talks, which we hope to bring to you. Excellent speakers who are really preeminent in their fields. So I hope you will join us and benefit from them in the future as well. Thank you.
Thank you very much, Professor Sandeep. Again, on behalf of the TIFR Asset Forum, it's an honor for me to welcome on my behalf to Professor Subhasis Chaudhuri, Director, IIT Bombay. I also would like to welcome our very own Professor Dipan Ghosh, the President of TIFR Alumni Association, and all of you for this very special Asset Colloquium. First, a few words on ASSET. For those of you who are joining from outside, ASSET stands for Advances in Science, Engineering and Technology. It had its origin as the Instrumentation and Electronics Colloquium way back in February 1983. Somewhere midway, we changed the gears of its organization. That was in January 2002. And it's a great tribute, I must say, to the Institute that we just reached this milestone of 750 colloquia organized in this new format during the 75th year of TIFR. So you have 75 years of TIFR and 750 colloquia of ASSET. Just a word on Engineers Day, of course, as Professor Sandeep mentioned, is being celebrated since 1967 on September 15th, which is the birthday of Bharat Ratna Mokshamanda Visvesvaraya, the most loved and well-known engineer the country had ever produced. Today is his 160th birthday, in fact. It's often said that he utilized every minute of his long life. In fact, you know, he lived more than 100 years for excellence of the nation. His contributions to engineering, industry, agriculture, education, even commerce and banking are too numerous even to list. His course on economic planning in India, that is Planned Economy for India and Reconstructing India, was the first available document on the planning effort of the country. And it is still held as the parent source matter for economic planners. Some of the past distinguished speakers of Engineers Day Special Asset Colloquia at TIFR are Dr. Satish Reddy, the chairperson of DRDO and Secretary Department of Defense R&D, Government of India, Professor K. Vijayaraghavan, the Principal Scientific Advisor to Government of India, Dr. G. Gautaman, former Distinguished Scientist and Chairperson DRC Safety Council. We are very fortunate indeed that this year Professor Subhasis Chaudhuri has kindly agreed to talk on machine learning and engineering perspective. We all would like to thank Professor Dipan Ghosh for proposing the speaker and also request him to formally introduce Professor Chaudhuri. But just before he takes over, let me please say a word or two about Professor Ghosh himself. Professor Dipan Ghosh is best known for his Mazumdar-Ghosh model which he developed along with his thesis supervisor, Professor Chanchal Kumar Mazumdar at the Tata Institute. He was associated with Bristol University, Northwestern University, University of California, Santa Cruz, and at Vishwavarati University before joining IIT Bombay. He was the deputy director of IIT Bombay during 2005 and 6, and was the president of Indian Physics Association between 2005 and 2007. So with those few words, it is now over to Professor Ghosh and then on to Professor Chaudhuri. Thank you very much.
Thank you, Dr. Satyanarayan, Professor Chaudhuri, Professor Trivedi, and ladies and gentlemen. It's with great pleasure that I introduce today's speaker, Professor Subhasis Chaudhuri, to my alma mater on the occasion of National Engineers Day. The pleasure is much more because I have known him for over 2 decades as a colleague and a friend. And today he heads the Indian Institute of Technology, Bombay, as its director, where he started his career as a young assistant professor in the year 1990. Professor Chaudhuri graduated from IIT Kharagpur with a BTech degree in Electronics and Communication Engineering, the institute which recognized his contribution to engineering by honoring him as its distinguished alumnus. He got a master's from the University of Calgary in Canada in 1987 and a PhD from University of California at San Diego in 1990. Soon after that, he joined IIT Bombay, and his professional career spanning over 30 years at IIT Bombay, he has been associated, other than academics, with many, many administrative positions. He has held positions such as the head of the Department of Electrical Engineering, the Dean of International Relations, professor in charge of IIT Bombay Monash Research Academy, etc. He has earned too many awards and distinctions for me to recount here. And this include, for example, Santishwaru Bhatnagar Prize, Swarna Jayanti Fellowship, J.C. Bose Fellowship, Vikram Sarabhai Research Award, G.D. Birla Research Award, Nasi Reliance Award, etc., etc. He is a fellow of all 3 academies of sciences and also a fellow of the Academy of Engineers, in addition to being a fellow of IEEE. His research area, as was pointed out, is in computer vision, machine learning, and computational haptics. He has over 100 publications and has authored 7 monographs, all of which have been published by Springer, New York. He holds 13 national and international patents. It is with great pleasure I introduce you and present Professor Subhasis Chaudhuri for this talk. Thank you.
Thank you very much.
Thank you. Please go ahead.
Yeah, sorry. So I just would like to thank Professor Ghosh once again, and now it is over to Professor Subhasis Chaudhuri for his colloquy.
So thank you, Professor Satyanarayan. Special thanks to Professor Sandeep Trivedi, Professor Dipan Ghosh, and the TIFR people to invite me on this special day, which we celebrate as a birth anniversary of one of our most distinguished engineer. So it's really a great honor. I consider it a great honor. And the fact that my work has more or less dried up over the last few years as I'm taking up more and more administrative roles. So I thought that when I get always a chance to speak, why let it go? So I tried to cook up something which is based on my learning over so many, 30 years of being trained as a classical engineering discipline, but later stage trying to pick up this new paradigm of knowledge of machine learning and try to see that how I can blend it and give a presentation on on this particular aspects. So please bear with me for the next 50 minutes or so. So let me, when I take a title like machine learning and engineering perspective, yeah. So let me first, I have to explain what we mean by an engineering perspective. So let's look up something like, like an Alice trying to go down the alley. So we wanted to find out something which is interesting. So as a scientist, most of you in TIFR, you would probably try to dig deeper and deeper as you see the well above. And then if you look at engineers, we are trying to look at the one below. And please don't worry about the mosh attaching to that one, because I just picked it up from the internet. But the key thing is that our, when you look at measuring certain things or developing certain aspects as an engineer, we may not go that deep in terms of solving certain fundamental aspects in terms of the knowledge generation. But we are more interested seeing that if certain things are given, like for example, the lower picture that you see here, where if you wanted to find out that this is like, I want to find out what is the depth till at which I need to float my bucket to get water, I think this is good enough. I don't really need to know what is the depth of the well. So that's the kind of perspective that we are trying to talk about, because machine learning, in my opinion, is pretty much the way that we solve the problem as an engineer rather than as a scientist. So let me go a little bit deeper into this engineering concept of solving a problem. So let's look at more from like a system engineers. Normally, our life is controlled by three things, okay? One would be input. You will get certain things as an input. And of course, at the end of it, there will be some output which we are looking for or something unexpected. And it does pass through certain system, or it's a model, or in general, I can just call it a black box. And normally, so it can be given as a picture like this. So you have an input coming into a system, which spits out certain output. And normally, most cases, we're given two of them, okay, any two, and you have to find out the third aspect. So it could be a system identification problem if I just, if I'm given input and output, and if I have to find the system. Or if I'm input and system is given, then I'm more interested in finding out what would be the output. Of course, we make certain assumptions, which is quite inherent in solving all our problems. So these assumptions are part of life of all engineers, and hopefully they're good so that they meet the demand of reality. And then the question is like, all our life basically would be these three things. And for the time being, let's look at more under this particular system, which is we may also call it like a black box. So let's look at the same time, at the evolution of science, okay? Because finally engineering is nothing but the concept of science being used for engineering applications, for some technological applications. So if you look at, good old days, it was always empirical. You see certain things like, the boat floats, okay, even though it's supposed to be heavier, similar. But then later on, you do develop proper scientific theory, which is, of course, become very strong during the Renaissance, even before that, and slowly after that. But around 1950s onwards, when the computer came out quite strongly, then we had the third paradigm of science, which is called the computation science, where the model and the simulation becomes very important. It did help quite a bit in terms of solving a lot of issues. And now, I think for last 20 odd years or so, is the data science, where the data is supreme. And it's also now it is called the fourth paradigm of science, where we look at as a data as the key thing, both at the input, at the output level. And probably we are not so much engrossed into developing certain concept that goes in seeing that how the input translates into the output. So let's look at this is my, the gist of the talk would be like, as I said, that I started always in the classical training, where if you see a box, which is like we call the system, which is represented by a black box, and we try to open it out and see what's there inside, because that defines that what would be my expectation about the output given certain inputs. And this could be, in terms of system identification, in terms of certain set of parameters or certain other kind of models. But nowadays, as I said, the old order changed and will be in place new. We still, of course, we do have the black box because things pass through such a system. But probably we don't need to open the box. We keep it really closed because it turns out that we, in order to live a life to its fullest, particularly as an application engineer with machine learning as my domain, I may not have to always open the box. Okay, so we'll keep the box closed as of now. So let's go to the next one. Okay, so let's look at the machine learning as it is today. So here is this black box, which I'm just, look at my cursor here. So this, I'm calling it as F, and then you have an input data. And let's say you can have output either as a problem of a regression problem, or it could be a classification where you have certain number of classes. You want to say, which class it goes through. Now, this is in general the crux of the problem that most of the people try to solve. And during the past 20 odd years, what was found out that almost any mapping function, so F can be considered as a mapping function, almost any function can be learned. I think that's what people start claiming, of course. And if you say better the learning, better would be the performance. Performance means that, what is the expected or desired output, I am closer to that. So if the learning is good, that's what you expect. Now, how does it happen? So let's go to the next level. So the same box now, we said that F is now parameterized with respect to certain number of parameters called theta, okay? And what you need to do is that in terms of getting from the training to the classification, from the input data to a classification, I need to know this function F in terms of all the parameters theta. So what we do, we set up a kind of a loss function. So earlier days, we used to call it is a cost function, or you could have some other terms, but nowadays the common term is called the loss function. And we try to minimize in the sense that if you give some input here, and if you see some classification, how much is the error? So that's the loss. And then you try to minimize by using some kind of technique as typically, you can do some kind of a gradient search or some modified search, and then you find out what are the parameters of this, and now you have, in some sense, represented this black box. Now, of course, currently it is also being claimed that almost any cost functional L can be minimized. So that's a good point. But the choice of this loss function L is also important. That's where a lot of research does go in, because you try to play with it and see what it goes through. And what also matters is that this F is no longer like a nice kind of a model that we are trying, normally aware of, but it could be like a quite complicated network architecture. And this architecture is very important. So I'll show you that as an example. So a typical architecture would look like this, where you have an input coming in, so you have certain input layers, and then each one is certain weight multiplied by the input, and then at some point you have some weighted combination of all of them. If you go back earlier, there used to be called like Hebbian learning and others, so you just do some weighted summation, and then you can have some function after this, okay, and then this is the next layer output and keeps on growing. So how many layers you have and how many nodes have in individual layer is anybody's guess. Typically it's very, very large. Then it becomes like deep learning. And also I would say that as the number of parameters theta becomes very, very large, then you could clearly see that this system is almost like becoming a non-parametric system. So we're not really calling it as a parametric system. This would be like more like it's a medical science or something. How do we represent our human body? It's not just like parameterizable with respect to few parameters. There's a huge number of parameters. Okay, so it almost we give up the concept of parameter tuning and others. But at this point, let's look at a very classic problem which is there for almost like I would say 40, 50 years, which is a problem called a XOR problem. So it's a two-class problem. So you have a data, let's say this is 0, 1 and 1, 0 will give you something like blue. And if you have the other bit, like 0, 0, 1, 1, 1, then you will get the other one. Now, the question is that, can I have a classifier developed to separate them into two classes? So it's a two-class problem, but no matter what you do, you can prove, of course, you can see that I tried, like this is a classifier, it's a linear classifier here, or this is another classifier here. And it turns out that there is no linear classifier exists which can separate them. So, right, this is a very well-known problem. But the question is that, who tells you to use linear classifier? So if I use anything like this, the same problem, if I relax and say, okay, define some kind of a decision boundary, which would go like this, okay, any arbitrary, of course you can have any different one also, I would be able to separate them out. So I can actually do the classification. So I have a solution, right? So the message is that, of course, why not use a nonlinear one? And then when you try to do it, then you say, why do I need any linear model? Simply just why not trash it? Okay, because I know there would be a lot of problems with linear models. So let's not worry about it. So now you bring in nonlinearity to your system. So interestingly, what happens is that when you bring in nonlinearity, as an activation function, so that means when you have a weighted sum followed by certain kind of nonlinearity, and there are a lot of different names. One of them is called ReLU, so which is actually nothing but if it is negative, okay, so the difference is negative between the original and what is the desired, okay, whatever the output, then if it is negative, you saturate to 0, and if it is positive, you just keep it as a slope 1. Whatever it comes, you put it out. So it's also nonlinearity. Now this turns out to be very useful, and it beats all the difficulties that are associated with the linear classifier. But also what happens, as I said, the theta is large. There's a huge number of them. And many times we don't really have that many equations to actually solve. And remember also we are talking about nonlinearity. So degrees of solution would be very large. So there is no way we can have an exact solution for all the parameters. So it simply doesn't exist. You can't do it, okay? And naturally, this will have multiple minima, but it turns out many people worked out and say that any good minima is good enough. And maybe I can even relax it, any minima is good enough, okay? That's what most people claim, and that's where actually the machine learning stands today, okay? Now, given this, so where are we now? So they lead to the following. So you have a very large parameter space because this black box that we have now represented by a very large number of parameters, maybe million of them, okay? We have abundant nonlinearity, various different kind of nonlinearity. You can add at different layers. You can even throw away some of them, you can call drop off and things like this. We can use any kind of loss functions you can think of, okay? So it becomes absolutely like, in the earlier case, it would have been a nightmare to solve such problem mathematically, but thankfully, we can now solve most of it. So we would rather now come back here, and if you see this picture here, we are saying there's no need to open the box anymore. Just keep it closed. Okay, that should do the job. Okay, and then if you allow me to make a little bit of sweeping statement, I would say that make it a discipline, which is an experimental engineering. Of course, engineering has been experimental, but here there was always a kind of bottom line where you can predict theoretically what would happen. Now you were saying, let's try it out. Let's use this loss function. Let's use this kind of nonlinearity and see what happens. And if it is good, use it. That's what we do. Okay. Now, at this point, since I normally work on image processing and no image processing talk is ever complete without a picture of Lena, so I put it here. And let's look at another aspect. So when we give you an input, so input is given. Of course, I have no control on the input. But what I feed to the network, which is this machine learning neural network, now that's called the feature. So normally what happens, let's look at this particular image that I show it here for Lena. If I want to recognize that this is a human face or even Lena, Now, it turns out there have been a lot of work earlier also. Like this is one of the work of, the very famous work of Hubel and Wiesel in 1965, around that time. They said that our human visual system, you have in the primary cortex, if you look at, there is a directionally sensitive elements, which finds out basically which are the things that fire our, those directionally aligned cells, so that, I can actually feel or see what's there. Okay. Now, this is, of course, a tremendous kind of a contribution on the way that we human being perceive things. But what it relates to as an engineering discipline is that, look at it, it's basically nothing but, if you look at here, is a directional derivative of that particular one, you take it. Okay. So if you get it something like this, you will get a directional noise. So as we know the noise, I would like to get rid of it. So we can always have some kind of a smoothing function, like a Gaussian smoothing here, which would clean it up, and I will get a smoother version, okay, of these edges. And these edges turned out to be very useful, and in recognizing things in a building and many other places where you have a lot of these flat areas, it doesn't give you much information. So information was very low. Now, this is how people have tried to look at it. And we say, why not use the edge detected image as the feature? Because the number of, I would say the amount of information that you are actually feeding it will be remaining the same, but your actual data size is much lower, and it's a lot more enriching. So if that is true, then the machine learning people said, put a separate twist to that. So whatever we call it as... Yeah, please.
Can you take a couple of questions? They were there on the chat here. Can I
read
please.
That? Yeah, please, of course.
Okay, one question from Xiaomian. It says, how did you, I did not understand the any minimum good enough statement.
Okay.
Absolute minima, if not, what is, why is this different from fits, where we actually spend a lot of effort in finding global minimum?
Yes, of course. See, the problem is there have been, if you look at the parameter space, it's a huge number. And if you look at the number of local minima that you have, is also, it's a huge. I mean, of course, you could say like, it's an infinite, in terms of number of this. Now, the question is that, of course, some of these, logically, we would think that some of these minima would be just a very, very, weak minima, in the sense that you are very far away from the optimal case that you would like. But as you say that here, there is, although there is something called stochastic gradient descent to come to a little better minima, but normally there is no attempt to see that you go to the, what I would call the global minima, because this would be in that case some kind of an, you do random optimization others. Those are not really so used. So statistically, I think they did some experiments. As I said, this is more like an hand waving statement for me, that they found that almost any minima, once you find it stops, you can take it as a, that it's deep, because sometimes it's also very shallow. So if you move around too much, you don't get out of that also. So you have to be happy with that, or you change the, the corresponding architecture and try to use it. So I don't know whether I've been able to answer that question. So if you say mathematically, am I right? Of course, I say no, okay, because you need to get a good minima. But here, because of the computational and other problem, if you feel the way you do it is that you do some validation on a validation on some kind of a separate validation test set. And if you find this is not good, you simply use something different. Say that this is, there is no good solution for this. Am I okay?
Okay, they've typed in a question. So maybe if there's follow-up, then I'll get back to you.
Sure,
Just one quick question from Akash Pandey, I think. Why do we use loss function only? I mean, I may be interested in knowing how close I am to the actual thing instead of knowing how far I am.
Yes, so I'll come to that a little bit more. There have been some constraints also they put in, okay? Yeah. So I'm slowly developing the whole thing over there. So let me just, I take it up a little later on that, okay? Yeah. So if you look at now, so what we said is that in the previous case, if I just go back to here, what happened here? So this was our model, right? This is how we were doing it. Now let's do a, because we realize the features is also important. So what we said is that why do I have to follow, this Hubel and Weasel's model? Okay, it's old model. So let's put this inside my optimizer here, right here, and also tweak it so that we can have a joint optimization of both this C, which is the feature space, as well as the parameter space here, and then try to come up with something. So one of the way of doing it is called CNN features, convolutional neural network features. And that means you give the input image, and after that you have layers of certain convolutions, and these convolutional parameters or an edge detector, which could be some kind of a differentiator. Now, instead of that, have anything, okay, any kind of weight, which would be a weighted combination, and just get that also as a part of your learning. So that's what basically is called an end-to-end learning. So where you put this as a feature, and this is the feature that you pass it through the network. So there is no more handcrafted data. So the feature, or rather handcrafted features. It does give you, because you are doing a kind of a convolution, so it gives you certain translational invariance, but not rotation. So there is a way they take care of a little bit of rotation by, manually moving a little bit here. But see, what normally I find that, this is fact is mostly ignored in machine learning, is that the convolution would always lead to shifting of the edge. So edge localization doesn't happen, because if you look at where is the derivative going to max, or the second derivative going to 0, it will shift it. So there would be an effect. So if I want to do an estimation of certain parameters in terms of what direction a camera is viewing, I'm sure that would actually affect your accuracy. But to some extent, if you look at it as a classification problem, it doesn't affect. But some estimation method, it does affect. Okay. So let's go to, so now we have the features. We have the black box. Now let's look at why is this ML craze. Okay. So first thing is, of course, most often than others, that it offers better results. That's what people find. Codes and data are publicly shared. So almost, anybody writes something, ideally, I'll have access to that to even run it. Can be used as a plug and play system. Interfaces such as Python are very simple. Any even 12th standard kid can do it. You don't need anything. It's parallel and GPU computable. So even the code banks, all of them are available. And no specific user expertise is required. Now, which could be dangerous in some cases, because you probably miss out the physics in the problem. But I've seen people just solving it purely as a plug and play device, and sometimes coming out with even results, which I think normally it's not allowed. I mean, this is not allowed in the sense that something I know that the solution doesn't exist, but they can come up with something. Okay. If you have a question, I can answer to that later. Okay. Now, what happened to at this point? Let's look at in 1980s. See, this artificial neural network and others. It was been there for earlier also. Okay. So, there was a claim that neural network mimics the biological system. Okay, and that's how it got a lot of emphasis. And the second one was that graceful degradation. So that means if you have a big system and some of the nodes fail and others, you have a marginal dropout in the performance, but it still works. But as an engineer, since we are looking from that particular perspective, why would I care if I have to get a job done, whether it is done as the way the human would do it or a machine would do it in a completely different way? It probably doesn't make any sense in the process of the job getting done. So this process nowadays, I don't see anybody further claiming that the neural network is actually what is the original neural network in the process of biological system. So I think that's something where we are very much different from how it started getting developed. Okay. Now, this is where the difficulty is that the training may take a long time. Okay. This is one of the, sometimes it takes days. Okay. In some cases, even months. Okay. There are problems with over and underfitting problem. This is a typical problem in data analysis. Choice of loss function is important. Okay. This is where the question is that, you can try with that, but even in that case, just choosing a appropriate loss function is not enough. You have to add some constraints, okay? Because the weight space is too large. So what you do, you can add certain constraints, okay? And these constraints, one of the common thing, if you look at the classical, let's say the mathematical problem of like a ridge regression, okay? So normally, if you have to invert a matrix, which is where you have a problem, okay, because of conditioning. So you add certain kind of thing as a, on the diagonals to make it better, well behaved. So if you put constraints like, certain L1 and other constraints, actually it moves the solution space in such a way so that there exists certain solution, okay, but, it moves away from some of the weights being completely atrocious. So they look at certain kind of constraints. Okay, I want the total sum of all the weights to have some minimum value, like this. Okay. Now, types of learning. If you look at, there are different types of learning that happens. One of the most common thing, okay, is the supervised learning. So you give some training data, okay, and you get it learned, and then you use it on actual other real data. Few shot learning is that I have very few training sample available. So training is difficult. So basically you train on certain thing else and then reappropriate it for other cases where you have only very few training data. Then you have a zero shot learning. That means I don't have any training at all. Okay. But I have training data for certain different kind of things. So for example, I have training data for cats and dogs, but not for bats and hogs, let's say. Okay, so I would train it for cats and dogs, and then I would say, okay, maybe bats will have wings of, a cat. It looks like cat, but with some wings or something like this. So it will be a bat. So it tries to do it. Maybe I'll give you an example of this, okay, at a later stage. Reinforcement learning is very popular because where you do sporadic reward and punishment scheme, that's, it has picked up tremendously over the last few, I think last decade, I would say. And everybody at the end tries to do unsupervised learning. So that means no training is available. It should learn on its own, and which is very difficult, but there have been cases where some success has been achieved. Apart from this, there is another kind of thing that is also getting very popular nowadays. It's called the generative adversarial network, okay? Now, what it means is that, and I'll give you a simple example here, that you have some real scene from which you are sampling. Okay, so that's your observation. Now, at the same time, I want to create a model that actually creates, like, it mimics that particular, the observation space so that I get an estimate of that observation. So what it tried to do is that we try to equate this in the class. So that means they belong to, let's say, both of them as a human face. Okay, so I'll show some examples of a human face. And here is a model, which is our neural network, which will try to generate from the random noise as a perturbation, some estimate or some kind of an example of a human face. It doesn't have to be the same face, but it's a face. Okay. And so what it does is some kind of a density estimation to see that, this is the whole thing. And so this is the generative process. So where is the adversarial process? That happens in the, okay, so you can make it class conditional here, which means that it's the same network I can create for, if given on some kind of a conditioning that, okay, I want to generate images of cats or images of dogs. So that's the condition, and it can generate that kind of thing. Now, what is the adversarial training? Is that if you, here, so here is a real world is a face image, and your generator, which is what I'm learning, is actually if it is this one, looks more like a face. So there is a discriminator, which is also I'm learning. So this discriminator, if it finds that, yes, they look the same. So then of course, you say that my generator is doing good job, but discriminator is not able to discriminate. So let's improve the discriminator. So we learned this part. But if it says it's fake, like this particular case, then it goes back here and says, okay, you improve the generator. So this is how you do it. Now you may say that, when I give you an example, which is like almost a limit to see what kind of people have done it. Okay. Let's look at some really non-trivial problem people have. So this is not something that we have done, but people have done it. Okay. The first one, okay, it's very interesting. Okay. And that's an use of this GAN, the network that I just talked about. So if I actually play some sound, okay, some music, let's say, so it's called speech to face, and it can actually give you a picture of the face, how the person would look like. Can you imagine that this is happening? That, I just give you like some speech samples, okay, and I can actually view it. Like, let's say of course, I know that Professor Dipangos has a very different kind of speech, and I can make out, but still from that, I cannot make out what would his picture look like unless I know him personally. And this has been done by one of the very well-known person like Freeman's group at MIT, okay? But so that means I can actually learn certain kind of, generate pictures of things that almost looks like there's no connection. But, on the other hand, you can actually ask the question, supposing I give you Professor Dipangos's picture here, and can you create his speech sample? Okay, it turns out that doesn't work well. So even though normally we say that the, picture is worth 1,000, sentence words, actually you find out picture is easy to generate rather than a speech sample. It's probably, my understanding is the phase which is not able to create properly when you do this kind of adversarial training. Look at the second aspect here. Supposing I give you a picture of this one, okay, and it simply looks at a picture and say, okay, what is the calorie content in this food? Okay, so people have done it. Third, I don't have the, I've seen this being referred somewhere, but I could not recollect the, the exact, I would say, the reference. But if you get a picture like this, now can you tell me like how much weight the person is carrying? Okay, so actually people have done the estimation of the weight of the load by looking at the picture, how much the person is actually bending. Actually, that's basically a way they do it. Okay, so people have done a lot of interesting things. So what we tried to do here, we said, let's do one problem. As you know, in Mumbai, one of the colleges very recently becomes very interesting is that, the Bombay University has an attendance problem that you have to have minimum number of attendance, and some college, there was not any kind of attendance, was very poor. So they said, okay, the students filed a complaint. How do you know that the professor is marking me absent? So they had a fingerprint, okay, detector so that your attendance was biometric. Now it turns out again that there were no attendance. Okay, very few people were attending, but everybody was given attendance. What happened is that they created some kind of a nice kind of gel on which the fingerprints were all learned, and they put it on that, the fingerprint checker, and they all got the attendance. So this is called the spoof detection. So there are spoofs. Now it turns out it's very difficult. Almost any spoof passes through automated fingerprint detection. So almost like 98% cases, it doesn't work. So you can actually create something like DeepRodNet where you look at the minutiae and few others. So you just pick up these points and train it. How it is doing, frankly speaking, I can't tell you. Okay, but when you train it with enough kind of data, we could actually see that it does pick up these fingerprints, which are actually spoof. Okay, so the idea is that before you use, this for your attendance or anywhere else, there will be a separate module which will do the spoof detection. If it passes the spoof detection test, then it goes to the next round. Okay, let's take the zero-shot learning. Okay, so here, so this is like a special database called CUB. I think it's Caltech and UC San Diego BIRD database. That's what it stands for. And so you have been given two kinds of classes.
Hello.
One is called a scene class, the other is the unseen class. So that means you have, let's say, 10 different birds classes, their pictures are given, you can train them, like which bird is this. Then you also have some birds here for which, you know, like let there maybe 5 additional classes for which you have not trained the network, that the system doesn't know. The question is, can you still identify them? Now you will say that how is it possible? Now look at the motivation comes from the fact that, you know, let's say supposing I see kind of a horse type of structure, but I tell my son that, look, if something looks like a horse, but it, you know, it has like a stripe pattern, black and white, then it becomes a zebra, something like that. So I don't have to show them an example of a zebra. So it learns from this additional description. So idea came with that. So what they do is that you have given some input of, you know, train the system with this, all the scene classes. And for each unseen class, they give you certain kind of a description, like normally they call it a prototype. And this prototype here, if you look at it, is called like an A. And then what you do is that you get some image here, and then you say, okay, I taken a latent class. So that latent class means somewhere inside, you have a smaller feature space over which we assume is normally I would call it a sufficient statistics to take a decision what it is, okay? So this kind of thing, what you take it, and then you pass it through, you know, there would be for each class, there would be kind of a vector, which they call it a prototype. So basically, you know, for each scene class, you map the, remember we said that any functional mapping can be learned. Okay, it's a claim. So if you map each for class of image to one particular prototype vector, then hopefully under the same mapping, this will also map to the corresponding prototype vector A for that particular class. Okay, so if that happens, so I train only on this, and for this one, I do only the testing, and it will map close to this. So you do like a nearest neighbor search for in terms of the prototype, and see whichever is the closest prototype, you say that this is my particular bird A or bird B. Now this is called zero-shot learning. Now this has become very popular. Of course, the key issue here is the prototype. Who gives you the prototype? Okay, so turns out that this particular prototype could be like a word-to-vec representation. So I'll come to that. Maybe some of you may not be very familiar, but I'll just explain very quickly that if I want to embed my entire set of the statements, all the words that I make into some kind of embed on some n-dimensional space by using some kind of a training, then that means that my word has a vector representation. And people have done a lot of nice things and showed that this thing is pretty good. Of course, this works for mostly for people like us talking. I don't know whether, you know, if Shashi Tharoor talks with his very specific kind of English, where would be the corresponding learning for the word-to-vec vectors. But for most of us, it does work. Okay, that's the claim. And this is also claimed to be the semantic information. Semantic means that I'm telling you what it is, okay? So the question that we ask at this point is that, let's look at this semantic information. So, yeah.
Can I interrupt you by a couple
Sure.
of questions from YouTube?
Yes, please.
These questions might correspond to slides a little earlier.
Okay.
So what is the difference between entropy and information gain in machine learning? And how to ensure that our model is not overfitting? These are the two questions. If you
okay
to answer later, it's also fine. But
I think we'll take it as a later stage, because
okay.
This is okay, because this is, I think, in general, these are the standard questions. Okay,
yeah,
that because of the training, we'll come to that later. And just remind me in case I forget. Okay.
Yeah, sure.
Okay. So let's look at something interesting about people talk about semantics. Okay. So here is something that, let's say I have a picture of sofa, okay, here. Now, I also additionally give you a picture of something, so the word-to-vec representation, one vector. Now, the way I do it is that I map that to the word to vec and then give it as a combined one, or I just as an additional feature. And then if I say what would be the same thing, I do it for cat and then the word to vec representation of the cat. Okay. And then supposing I say the find out the accuracy of the classifier, if I don't use this particular word to vec, that means the semantic information. Okay. Does it help in improving the accuracy? Now it turns out that most people say, yes, there is a good improvement in terms of accuracy by putting this kind of semantic information, right? So my question there at that point is a very classic question, what's in a name? Okay. So supposing instead of sofa, I use something divan or something else. I mean, I just call it in, I don't know, maybe cat in Bengali, I call it beral. Okay. So the representation, word to vec representation could be completely different. And then would that be the same? Does it make sense? So during this lockdown period, so I just asked my son to do the following. Okay. Let's switch this. Okay. So I put the, image of sofa with the the semantics of the cat, and that the image of cat with the semantic of sofa. And now we compare the same thing. Now, what do you expect? Do I improve this accuracy, or should it be worse? It turns out that I still get better. Okay, then what does it mean? Okay, so what is actually the vector representation probably has no real relevance, even though many people claim. Okay, and those of you who are familiar with the normal, like in a traditional vector space, there is something called null-Foley-Salmon transform, where you can actually show that if you have in a small sample space, whereas the dimension of the feature space is very large, you can actually map the entire training data set into a single point. Okay, but it does not guarantee that when you are seeing something which is different, that means the training, it could be very much away from that. Okay, so normally my classifier should work on the data which it has not seen. So there the performance is more important. So this allowed us to think a little loudly that probably this has not so much of role to play. So why not do the following? So here is something called Booknet. Okay, and in machine learning, everybody is familiar in calling very arbitrary kind of net. So this is Booknet. It's a guided clustering, based network. So let's say I have a very, very difficult, cluttered data set that I need to classify. Okay. So why not I put something where, let's say I have a very good, well-separated feature space. Okay. And there exists certain kind of data set where the performance is almost like 100%. Okay. Like one of them would be like this, the digits. Okay. That people use. And now what we can do is that we can use it in some sense by saying that this data set should be mapped like, one class to this one, the other class to this guide. And if I try to train a network, then ideally they should get better separated. So this is being used as a guide. Okay. And guess what? It turns out that I can gain around 5% more accuracy, even though this has like, earlier it was like 80, 85%, it goes to close to 90%. And secondly, we randomly permute that who should be guide for what. I get pretty much the same. Okay. So it basically, it's happening that because we are trying to separate the feature space and the mapping function is working fine. But what happens here that supposing I don't have a proper database, can I use simply like a vector space, as I said, as a prototype? And they are well separated. Now you can use like, typically like a Hamming distance between the data set to be little large. And then you just use them to separate it out. Now you see that they get little separated out. And again, I do gain. So that means by guiding this cluster, which are very, very clustered data set, I would say the cluttered data set, I can improve. Now, of course, at this point, I cannot answer the question, which is very natural for anybody in a computer science would be saying that if there is a topological matching between the subspace, for each class with this particular one, then probably I can improve. Of course, I agree to that one, but my point is that I do not know how the feature space is mapped. So the topology gets defined because the feature space itself evolves. So that's where, but otherwise, I have a feeling that it could actually improve. So let's go to the next one. Let's show you some example where let's say a video where you have, let's say, some number of frames, and you want to do encoding. Like, for example, right now, this platform automatically does something to save data, right? So your data compression. Or it could be something like a hyperspectral data. You have multiple bands and you want to compress, or you want to capture it with something, let's say on some kind of a drone where I have very little power, okay, or very little even your bandwidth available for transmission. So we want to develop like a acquisition system. We are calling it like 1-bit your compressed sensing. So what you do is you take the video frames, you take one arbitrary from here, one data from each one of them, and then take the next pixel from the next frame, like this, and collapse into a coded snapshot. Okay, for every, let's say, 16 of them, I code into one. And then again, remember, it's an 8-bit data. So I can actually say, I do some quantized thing. So it's a 1-bit. Okay, so I can do some other way of doing this, the generation of 1-bit data. Now, this is my compressed data. Now this, I send it to the receiver. And it turns out that since I know at this place how, if I can train the network by showing this and this as the desired output, actually the network can be trained, and I simply, the receiver has to know what is the network, and it can generate this from the output. So your basic mathematics looks like this. And as a matter of fact, originally this problem came up as a compressed sensing problem, I think was done in 15. And the general solution is to use orthogonal matching pursuit. And the problem there is that it's a computationally, it used to take a lot of time. So it was not really good for any practical applications. But here, the training also doesn't take too long, but the generation is, regeneration, this is very quick, and no computation. Look, this is just some add and subtract, nothing else. Okay, so there is so it's very, very energy efficient. And secondly, it's very quick because there is no, any kind of compression engine has an inbuilt decompression engine because they want to do some residual encoding. So this doesn't have anything. So we find, I can show you some example here. Let's say this is the original video. This is the typical, whatever the latest, your standard thing called HEVC. Whereas if you run it on 1-bit, see as the proposed thing, you can see that this is definitely not so bad. It, of course, is supposed to be a little poorer, but which you can see near the ear portion here. So I play it here again. So, but it's not so bad, but it's very quick. I'll show you here. What happened? Oops. So if you look at this, so performance-wise, so they are like almost very close depending on what bits per pixel I'm using. And similarly, if you look at the time, so typically it takes 7 seconds for a normal compression engine. Whereas if I do it with the proposed thing, it's just like only addition, subtraction, and it takes a little bit of time on entropy coding. So this should be like around 4 to 5 times faster than this. Okay. So that we found quite useful. Okay. Now, the other thing, let's say, supposing, I'm giving you some examples of where it stands, but so for example, if you have a, now surveillance scenario, let's say in IIT, you have a main gate and market gate, then you have the department buildings. So you see somebody coming into the main gate, and then whether the person is entering into the physics department. So this is completely a different place, different kind of ambience, and you want to see whether the same person has gone in, because at the end of the day, you want the person to leave the place also. So I am not interested in recognizing that particular person, but I wanted to find out whether a person A has come in and gone out. So it's called person re-identification problem. So, if you see some examples, they look very different. They are from different viewpoints. Their, illumination could be different, occlusions, all possible things would be there. So it's usually a very difficult problem. But we actually came up with something which is following our traditional knowledge of like, normally RNN, which is a recursive framework with a neural network, is good, but we simply said, why not we put a moving average part, which is common in ARMA modeling. And we found that we can actually still improve the performance by around 4 to 5%. So I'll show you an example like this. So where this is basically a video of a query, whether this person, and from the database, it says, okay, this is the one which is closest to this. Okay, and these are the next rank, this is the second possibility, third possibility, like this. Similarly, if you look at here, this is the corresponding match, okay, for this one. Now, here, the other thing which is very common is the activity recognition, where you have a group of people, they want to move around and see what they're doing. So I can actually see that it's quite easy to do it here. See, if you look at the color of the box, if it's the same color, that means they belong to the same group. And at the below, it says what they're doing, walking, standing, and others. So, so this is a waiting, then talking, now you're moving. So all this can be done quite easily. And learning is a lot easier rather than using in a standard method, okay? But notice that there is a cyclist which is coming at a much faster rate, but it says it's walking, because here the speed of is not a factor. That's why it doesn't pick it up that something is moving much faster, okay? Now let's give you another example. Okay, by the way, if somebody wants to see what is the network architecture, it looks like this. I don't know what it means if you drop 1 or 2 layers, whether it works same or not. Probably it'll work the same way, but it's a good way of saying that it's a complicated network, okay? Here, let's look at the other way, that supposing somebody is doing abnormal kind of activities. So is it abnormal? Let's say here, this is a normal case. We are predicting this is how it should go, okay? So if it doesn't happen like this, so that means it's something which is abnormal. So look at this, we have simply given the data. There is no other thing, and it simply says that, okay, this is how the person is moving. So using this, now we go into the next case, say that, how do you find abnormal activity? Here, if you see somebody is coming here and this guy throws something, so this is abnormal. This is not supposed to happen. Now, this one here is the person moving. So blue is the predicted one, and the one you have, the green is the actual. So if there is a lot of difference, then that means there is something unusual happening, then it puts a flag. So you could actually learn this one. Now, okay, next I go into probably the topic is quite interesting, and then that would be probably the last thing that I want to talk about, is that supposing I give you this set of images, okay, what would you say? So people would say that, look, photographer was looking for something like a tiger, okay? Of course, in one case, there is a random thing, something different. But the question is that, can I say that what is common across all set of images? So this is a network, we call it again, there's a nice name called COSEGNet, okay? Where actually you train 2 things. This is, by the way, it's called Siamese. It's called conditional Siamese network. So the conditioning is that whether this and this, these are the 2 things within which you wanted to find out whether this is common or not. So if they are common, so that means you are doing a decision that the 2 objects are same. It's called a decision net. And the other one is finding out the mask. What is the common region? So that's, if it is same, then you update. Otherwise, you update only this one. So you detect the common object. And when it is different, you train only this part, but not this part. So that's basically the issue. And if you see pictures here, you can actually find here that this is an unsupervised method. And here you do a lot better to extract what is common, even though their color and other things are different. Okay, so it finds out. Similarly, now you can say that, can I reduce the number of examples? And also, instead of comparing 2 at a time, Can I have more number of images? So you can actually have something called a guide set where I show a lot of examples, but they are not for just for training. And then I give you the actual set of images here, and it finds out what is the common thing. So I'll not go into the details, but if you see here that I can actually find out these horses here, and there is a person here, it doesn't detect that because we are looking for horses. Similarly, in the second case is the plane. And if you put something different, it doesn't, it simply says nothing is there. So basically you can actually even capture, like for this case here, also here, this is not a horse. So you can actually find out what are the outliers in the data also. So there are a few some examples like this, okay? So I think, I gave you some examples to explain that, machine learning is very useful as a technology. And we also said that handcrafted features are not really that relevant. You should do end-to-end training, which will give even the features are also properly done. So these are good things, it does properly. But the bad things is that occasionally it does fail, and the failure points are not known. So you do not know how you're going to fail because you are not able to give some performance guarantee or performance bound, and not possible to give it in most cases. Now I'll try to explain this with a little bit cases that occasionally comes up as, some failures are not only poor, but it could be catastrophic, okay? And particularly, let's an example, like, you're searching something for shopping or something in a Google, and let's say I have a, my shoe is bad and I wanted to capture, get something, looking for something. And of course, Google is also looking at something and is trying to find out what it should give me an advertisement of. Okay, so some, put something. Now, let's say, as I said, that my decision boundary, because, we have done some training, okay, could be because of overtraining or it could be something different. I trained my boundary, decision boundary looks like this purple color here. And this is the open set, means everything else, okay? Now, out of that, one particular kind of an object class may have something like this, because you do not know what is actually the proper representation of the feature class after learning. So it may happen that, this particular case of when I'm searching for a shoe, and because I get a particular picture for which the feature, after the feature transform, you end up being somewhere here or somewhere here, then it's actually, it detects this as somebody else. Now, of course, for the presentation, I'm showing you a picture of a baby, but in some cases, it could be something really bad. Okay, so that's when it becomes like a catastrophic failure. Okay, so this is something which I have no idea that when this should happen and how to prevent that, because I have no idea of what is my decision boundary, because in this space of whatever, some 1000 dimensional space, how the space has been carved out to something to show that this is the, the kind of region which corresponds to shoes, okay? But of course, if you are doing in a regular kind of a classifier, like a linear classifier, I know what would be my classifying boundary, and probably I have a better control. Of course, I know that many times I miss out some dirty shoe to be being classified as a proper shoe, but it will not be as drastic as in the other case. So recent emphasis is, of course, if you look at that, unsupervised learning is something that is going on, okay, because getting a lot of training data is very difficult. So they try to do something explainable of AI, which means, like, go back to this box again. I said, we'll not open the box. Now at this point, we would like to open it and see whether we can make out something out of it. If I have detected a cat in my picture, why was it detected? So it should actually show somewhere that this is the part in the picture where there are some features of cat. So it should, so people have been trying to do that. There have been some success, not much, but I would say there have been some success on that. Other thing is that edge and embedded machine learning, where I would like to do it on a small kind of a device, which could be on IoT and others, which will not give you so much of power of computing, okay? And what is quite poor in terms of as a machine learning, that if you look at we human being, of course, we said that what we learn has nothing to do with the biological system. We have completely said different from the machine learning. Our learning is always incremental. You know, if you learn a lot of things, the next one is learning is easier. And of course, we don't necessarily forget the older things. But in the proper case, let's say supposing I have done a 10 class classifier and I bring in a 11th or 12th class, what happens? Turns out that learning this additional thing means, do I retrain everything? And if I don't, then I keep on forgetting the old ones. I may retrain it for the new classes. And this is a very difficult problem even now for the machine learning. So the take-home point, okay, and this is what I wrote in my abstract, is that at the end of it, during the talk, I said I have a black box which has done this job, and I have designed a black box, but which is my machine, so it has learned. But the question is, did I learn? Or what did I learn? Very frankly speaking, what I learned is that how to build probably another machine which will do another job X, but I do not know how the job is being done. And this is what struck me quite a long time ago when I had a student, okay, whom I asked, like, okay, can you, he used to come, as an undergraduate student, can you give me some problem? I used to give him some problem. So once I told him that, okay, why not look at this machine learning problem? So this person, he does something and he explained to me. I said, good, okay, now he says, give me another problem. I said, why not you do something implementation? He says, sir, I found out that, during this process, what the machine has learned, but I did not learn anything. So basically, I am copying what the student told me a long time ago, saying, he said, that's why I do not want to take it up. So I said, okay, good. I'll not give you something on machine learning. Go back to the classical problem. So thank you very much for your attention, and I'll be very happy to take lectures. And these are some of the students who have been working with me for last few years, and as well as some of my colleagues, Biplav and Sayan. Rajbabu. Thank you very much.
Thank you very much, Professor Subhasis. So there are quite a few questions. So let me start with Professor Vandana. She has a question. Vandana, can you ask your question?
No, I just give a clapping remark. It was a very nice talk. I don't have a specific question. It was a very nice talk.
Okay, sorry. There is one from Professor Vivek Datar.
Yes.
Yeah. Can you hear me?
Yes,
yeah.
Yes.
Okay. My question, maybe it's a little too audacious to ask, but do you think at any point of time, machine learning or maybe its developments might ever discover a theorem or a law of science?
So theorem proving has been there in computer science, automated theorem proving. Okay. So I think, but here, what I understand that some people now are using machine learning and others to even find out, I found something interesting. One of our colleagues here did in chemistry on finding which chirality works better in certain cases, even, and how the specific chirality can be produced during a chemical reaction. So I think they may be able to do it, but they would not know what they have done. See, this could be an issue, and see, what is the value of the theorem if you do not know what it means? Yeah. I think when we talk about a theorem, it's basically we understand, through the theorem we try to understand certain phenomena, certain basic thing. So if some theorem comes out and if you don't know what it does, well, it's a meaningless, I think, in terms of application wise. Okay?
So it's really unraveling the black box that is important.
Yes, I think to us, I think that's what we put more emphasis. Particularly if you said theorem, yes, it definitely, the black box has to be open.
Okay, thank you.
There's one question from Hariom. What is the failure percentage in machine learning?
Okay, so this is, okay, I did not say one thing, okay, which is, because that would be kind of a sacrilegious in terms of saying that. See, if you look at the current publication trend in machine learning, okay, there is only one agenda item that people look at it, okay, whether your system, whatever you have proposed, okay, has it beaten the SOTA, okay? What is SOTA? Is a state of the art accuracy, okay? So if if I am particularly in good conferences, which are of course very difficult to get in, so I have to show that my method works better than all previous methods, okay? And personally, I feel it defeats the purpose of science, if not engineering. And so you do a lot of tweaking and you keep on increasing. And sometimes, you have no idea. And I can tell you in one particular case that when certain papers are written, by reading at the paper, I have no idea what kind of accuracy that I am expected to get. So is it always correct? The claim is correct. That I could always say, unless the codes and the data sets are available. So most machine learning applications are data specific. So they report your performance on a specific data set. And the moment you give a different data set, then the term is called that I need to do domain adaptation, because it has not been trained on that particular data, and the performance may degrade substantially. Even if you get half or 60% of that, so you'd be happy to do that. And this is where the problem is. It is very, very data specific. So I may get in certain cases 80%, 90%. Even sometimes they say that I get accuracy more than a human being. So you have to take it with a pinch of salt, because you change a little bit. And it just, of course, that happens in a classical pattern recognition also, to be fair to them also. But it's very specific. So I cannot tell you that this is the accuracy is always like, say, 80% or 90%, that data dependent. Is that okay? And also how many classes, and basically interdependence, whether the fine grained classification is required or not. Okay.
Okay. Chaudhuri, there are some couple of questions I want to take from YouTube.
Sure.
I think one of them was asked a little before.
Entropy and what is
entropy and information gain in machine learning.
So, see, the entropy is quite a useful concept. They do it as a, the cross entropy. Basically, it is used as a classifier that, when you have 10 classes and you try to do, basically, it should go into one particular class. So it's in a distribution. When you try to generate, you try to see that it goes into something where that particular class, then, basically, I expect certain kind of distribution of my output, which is, let's say, focused on one or two particular, it could be single class classification or multi-level classification. According to those two classes, there will be pick, and rest of them it's not. So you do this kind of entropy used as a loss function, okay? So if you say entropy gain, you have to see what do you mean by entropy gain. So are you generating new knowledge somewhere? I did not understand the question on entropy gain, because we normally use entropy as a loss function, particularly for sometimes as a classification, but that's not the only loss function. There could be additional loss functions also.
Another one, can the problem be broken into parts and solutions recombined via machine learning to reduce failure?
So then you have to go for Gestalt theory or something, whether you do it in parts and they combine. So not sure I understand the problem clearly. Let's say, in classical pattern recognition problem, I could say that there is like a tree structured classification. So you do it at a, let's say, broad level. You classify, let's say, all animal versus, like the plant, flora, and then fauna. Then you go to the flora part, you do further classification. Then you have like some kind of a tree structured hierarchical classification, I think they call it. And similar thing, if you look at in the machine learning, there is also something called you can also try to implement, but I don't think anybody has shown that it has become better. Of course, there is a new class of problem called open set problem, where you have data set which is not trained separately, but you, like in zero-shot framework, you try to first find out what is like the class for which it is trained and for the class of data for which it is not trained, and then you apply only on those. So there has been some benefit on that, but I don't think in machine learning I've really seen that. See, because finally it's a complete one black box. So you do end to end. So if you do individual blocks, then it's not going to be an end-to-end learning. So maybe it will not work so well. That's my understanding.
Then another question: what is your opinion on ethical considerations when it comes to machine learning and AI?
Ethical in many specific things means what? Ethics could come from various sources in the, the way you train your network. That time you need certain data. So whether the data is properly anonymized or not, or whether data should be given to that. Okay. See, any classification or something that you do is a discrimination, right? We call it like a discriminator. So discrimination is always unethical in normal life, right? But any work that we do, we have to discriminate. Like even today, in the COVID time, I have to discriminate virus, with the COVID-19 or something different. Okay, so discrimination is part of life. And again, as long as you don't put it in human or any other kind of things, on a race or sex or any other, I think that's acceptable. But when you put it other, that is your individual ethics, as well as a collective ethics will play a role. Okay. So.
Okay, there's one more question from Zoom from Uttam. Could we understand the black box through complex system approach?
Not sure what you mean. It is a complex system, but what do you mean by a complex system? So it's nonlinear, okay? It's a huge dimensional, okay? And there are a lot of constraints, everything. Constraints is, of course, on the learning process. It's a complex system. I don't know what is exactly the meaning of this question. Yeah.
Complex system approach. Yeah. So, okay. Please let me know if there are any more questions on the Zoom or also on the YouTube. Okay, maybe I would like to ask Dipan if he has any comments or anything to say at this time.
I enjoyed the talk is all that I can say.
Of course, so do we. So with that, so let me thank formally Professor Subhasis Chaudhuri for taking time to deliver this excellent colloquium on this topic of course, far-reaching applications, and he explained very beautifully, from very pedagogically, at the same time also bringing up many open problems, especially in the last slide, the issues that he kind of posed towards the end. And I think those are the ones which are going to dictate the progress of this subject in future. We also would like to thank, of course, Professor Dipan Ghosh for actually making this talk happen, and also taking up that difficult job of introducing such a distinguished speaker. Thanks to Professor Sandeep Trivedi for his very warm words of welcome. Thanks to Kishore Menon for his many crucial contributions in making this event happen. And thanks all of you, all the participants, for joining this colloquium. And as Professor Sandeep mentioned, there are many interesting colloquia happening at TIFR, and many of them are available online during these pandemic days. So please keep looking at on the web page for coming up talks in the coming weeks and months. So with those words, I would say good night and take good care of you. Thank you very much once again. Thank you, Professor Subhasis.
Thank you very much. Thank you, everybody, for listening.
Yeah, thank you, sir. Thank you, Deepan.